Hey guys, welcome to the Chapter 5 guided problems, and I'll just jump into them. So the first one is attached table provides 5 different distributions for the daily demand of loaves of sourdough bread at a local bakery. Identify which distributions are valid discrete probability distributions and which ones are not. So I'm going to open this in Excel. It's going to be really slow. There it goes. All right. So it's going to be asking us about each one, like distribution A, B, C, D, etc. So the first thing I need to do for this is to take a total or a sum of each of these distributions. So if we recall, in order for a distribution to be valid, it has to always add up to 1, right? Because each of these is a percentage. So for distribution A, we're saying there is 20% that the daily demand is 0, 10% that the daily demand is 1, 30%, etc. And so if it adds up to more than 1, it's adding up to more than 100%, then that makes it invalid. Also, if it adds up to less than 100%, it's invalid. Also, if any of our specific percentages here were less than 0, so a negative number, or if they were greater than 1, that would make it invalid. So that's what we're looking for. So for distribution A, we're going to say that thing adds up to more than 1. So we're going to say, no, it's not valid distribution because, let's see, because you have to read these carefully. Because even though each individual activity is less than 1, the total probability is greater than 1. So that's why A is not valid. All right, B. So B all adds up to 1, and nothing is greater than 1 or less than 0. So we're going to say yes. We go to C. Same thing, adds up to 1, and none of them are greater than 1 or less than 0. So yes, that's a valid distribution. D, we can see it adds up to 1.9, and one of them is 1.2. So we're going to say this is not valid because one of the outcomes is greater than 1. Yeah, that's the best answer. Okay, and then E, it doesn't add up to 1, so its total is less than 1. So we're going to say, no, that is not a valid distribution because, let's see, because the total probability is less than 1. And that's it. So there's our first problem. That wasn't too bad. Let's move on to the next problem. All right, so the second question has to do with binomial probability distribution. So it tells us to consider the binomial probability distribution with these parameters, okay? The probability is 0.3 and n equals 7. And remember that in a binomial distribution, it's either a success or not a success. That's it. There's only 2 choices. That's what makes it binomial. So it's like flipping a coin is binomial, right? So if we were flipping a coin, so we would say, instead of it being the probability of a coin being 0.5, we're saying the probability of success is 0.3 and the probability of failure is 0.7 for any given try. That's what that means. And then n is the number of times we flip the coin, 7 times. All right, so what is the probability of the following? So I'm going to create a little calculator here in Excel where I put in my P as 0.3, and then my N is 7. I'm going to put S for successes, and that's going to be my variable that's given to me here. So my probability with a big P So I'm going to do this, equals binom.dist, or binomial distribution. The number of success is 0.3. I'm sorry, the number of successes is going to be this little s. The trials, or the number of times I'm going to try it, is n. And then the probability of success is 0.3. And then I have to put whether it's cumulative or not. So this is kind of tricky. So with binomial distributions, if we're looking for an exact number, then we're saying it's not cumulative. We only want the probability of exactly achieving this. So in this case, we're saying we want to exactly achieve 3. So it's not cumulative. So when we want to find an exact number, we put false in here. And then we put our S of 3. So the probability of 3 successes out of 7 tries, when the probability of any one success is 0.3, is 0.226895. Now this wants 4 decimals, so I'm going to go ahead and have Excel do the rounding for me. All right, so here it wants the probability that it's less than 3. So now we can't use this false, we have to use true. Because we're saying, if we're saying what's the probability that it's less than 3, we're really saying out of 7 tries, what's the probability that it was either 0, 1, or 2 successes, right? Any amount that's less than 3. So that's the first thing we have to do. The second thing we have to do is we have to change our successes to 2. So whenever we do a cumulative function, we're saying, tell me the probability of this number or less. So since it's asking us the probability that it is less than 3, that won't include 3, it will include 2, 1, or 0. So by putting 2 successes and true under cumulative, that's returning for us the probability that we would have either 0, 1, or 2 successes. 0.6471. All right, and the last one is the probability that x is greater than or equal to 5. So this is tricky because I've already said when we do this and put true in here, it tells us the probability of that number or less. So if I put 5, that's going to tell me the probability that out of 7, our successes that we have either 5, 4, 3, 2, 1, or 0 successes. But it doesn't tell me 5 or greater. So what I have to do is put in 4, and that will tell me the successes that it is 4, or the probability that it is 4 or fewer successes, 4, 3, 2, 1, or 0 successes. And then to find greater than, I'll have to take, remember, every probability distribution has a 100% that it will be, in this case, either 0 through 7 successes. So I'm going to take 1, or 100%, minus our answer here. So in essence, if I say this is the probability of having 4 or fewer successes, so 1 minus that is going to be the probability of having 5 or greater successes. And there we go. So that's the second question. Let's take a look at the third question. All right, so question 3 has to do with a Poisson probability distribution. So that's a little bit different. Remember, Poisson distributions are used for things where we're measuring something over time. So in this case, it's 2.2 phone calls every 5 minutes. So our average is 2.2 phone calls, I'll say per 5 minutes. All right, so that's our average. So we're going to use, so to get our P, our big P, which is our probability, we're going to use this function equals Poisson.dist, and X, well, you know what, I'll label this one X, and then here I'll put P equals Poisson.dist, X, our mean or average is right here, and then again, cumulative, true or false. So So what we're saying is, when we're saying what is the probability that no calls will arrive, what we're saying is, what is the probability that we have exactly 0, right? So we're going to say false. If I could type this right. For our x, we'll put 0. So our probability that no calls will come in the next 5 minutes is 0.110803. It wants 4 decimals, so I'll go ahead and let it do the work for me. What's the probability that 3 or more calls will arrive during the next 5 minutes? So again, remember, if I put in 3, then that's telling me the probability of exactly 3 right now, right? If I put in 3 and put true, now it's telling me the probability of 3 or less. I want to know the probability of 3 or more. So what I have to do is put 2 in here. That gives me the probability of 2 or fewer. And then I'll subtract that from 1 to find out the probability of 3 or more. The probability that 3 calls will arrive during the next 10 minutes. Now this one's a little tricky, because if you remember before, our rate was per 5 minutes. So our average per 10 minutes would be double that. So we're going to have to change our average to 4.4. And now we want the probability that 3 calls. So I'm going to say x is 3. And then my cumulative is false because it wants to know exactly 3. So here it is. The probability that 3 will come in is 0.1743. And the last one is the probability that no more than 2 calls will arrive during the next 10 minutes. So that's still our average of 4.4. I should have changed that per 10 minutes. And then our x is, they want to know 2 or fewer, right? No more than 2. So I'll put 2 here. And then we'll change this to true. So it'll be or fewer, right? Because that'll be the probability of 2, 1, or 0. And so 2 or fewer will be 0.1851. There we go. And that's the end of question 3. And so one more to go. All right, so this last one, it doesn't tell you like the first two did, but this is going to be for a hypergeometric distribution. And you can usually tell these because it's going to have 2 different variables going on. So in this case, we have a bowl of candy, and it has red and green candies in it. And so because there's these 2 different types of candy, to find the probability, we'll follow a hypergeometric distribution. So there's a couple things we have to identify here. So it says, I noticed I've selected 6 candies. So it's, he grabs a handful, and it has 6 candies in his handful, and he grabs 6 red ones and no green ones. And you're probably thinking, like, as a statistician, that's weird. Like, what's the chances of that? So he says, let's say that there are 9 green and 10 red candies in the bowl. What's the probability of this event occurring? So our sample size, or we could sometimes call that n, is 6, right? Because that's the number we picked out of the whole bowl. And our sample successes, and here we're defining successes as grabbing a red candy, is 6. And then our population success would be the number of red candies in the whole population, which is 10. And our population as a whole would be the number of candies in the bowl altogether, which was 19. So we've identified these 4 things, and it took a little bit of work to do that, to say, okay, there was 19 total candies. Of those 19 candies, 10 of them were a success, or they were a red candy in this case. And in his handful, all 6 were red. 6 out of 6 were red candies. Okay, so now we can use this function, hypgeom.dist, and it's going to want sample successes That's what sample underscore S means, 6, comma, the number in the sample or sample size, comma, population successes, comma, population. Our cumulative is true. Whoops, all right, I did that backward. Our cumulative is false. All right, we would guess that this would be a pretty low likelihood of happening, right? If there's 19 candies and 10 of them are red, and I just grab 6 of them randomly, the fact that all 6 of those would be red seems like a low possibility of that happening. And that is borne out by our data here. It's 0.0077. Or in other words, 7.7 or 7/10 of 1%. All right, and just so you know, remember I said that we decided that grabbing 6 red candies was a success. We could switch this around, okay? And we could say, no, grabbing a green candy is a success. Then we would say, hey, our sample size is still 6. That's how many we grabbed, but we had 0 successes out of that 6, right? Because we didn't get any green ones. And our population successes would be the number of greens in the population, which is 9. And our total population would still be the green plus the red, 19. So we can see that if we do it that way, we still come out with the exact same number, 0.0077. So you can set the success either way. You just have to then identify your sample success and your population success based on that same factor. And our choices were either just to say red, grabbing a red candy was a success, or grabbing the green candy was a success. And we could do it either way and come out with the right math. All right, that's it for chapter 5. I hope the homework's not too bad for you. And as always, don't be afraid to reach out if I can help you in some way.